two announcements. First, please remember the lecture on the 2nd on FDI inflows in India. Yeah, that's lecture by Dr. Chandras Deshpande, who is currently at the Wellington Institute of Management, but he is an authority on the Indian economy. So we'll have that lecture at 2 o'clock on the 2nd in the Firoz Shah Mehta Bhavan auditorium, and all of you should attend that lecture. The next announcement that I have is, we are going to have a break from 5th to 9th, the Ganpati break. So on the 7th, 8th, 9th and 10th, there is a 4-day, full-day workshop on R. On R. R is an open source programming language. It's a free open source programming language. It is currently the basic language of programming in economics, in social sciences, in natural sciences, in mathematics, everywhere, in finance for example. It can also be used a great deal in simply analyzing data in various ways. So the 4-day workshop, which will happen on the 7th, 8th, 9th, 10th, which will teach you the following. One, which will teach you basics of R. R is a programming language, so you have to learn the syntax. It's not something which you can do by pressing buttons. The second thing that it will teach you is how to work with large data sets. How to filter data, for example. How to clean data. How to rearrange data using R. Yeah? Because most of the data sets that now we work with are very large. And given these very large data sets, you can't manually, physically go into and, for example, if you look at the NSSO data, National Sample Survey Organization, unit level data, then that's about 1,16,000, 1,20,000 households. There's data on 1,20,000 households on about 700-800 columns. So it's a 1,16,000 into 800 kind of, that's the dimension of the data that you have. And so you can't physically look at each of the entries. So you need methods to clean that data, manipulate that data, massage that data, extract various only certain parts of that data. Then you also need to learn how to visualize data, how to do graphs, for example, of this kind of a data, how to look at patterns in the data, how to understand patterns in the data. A lot of research work now happens using actually social media data. Yeah, you would want to, for example, if you are producing a movie and if you're showing trailers, then you would like to know how many likes there are for your trailer on, say, YouTube and Facebook, and what are the discussions going on in Facebook. So you would actually like to learn to read that data and analyze that data. And finally, how to do a simple linear regression in R. Right? Apart from some other clustering and those kinds of methods in R. Yeah, so that's a 4-day workshop. 7th, 8th, 9th, 10th, 9 to 5. Yeah, it's going to be done, a little bit of it will be done by me. A large part of it will be done by 2 professionals who are computer scientists. Yeah, one of them will be Sonali Nimkar, who used to be with Accenture in the US for about 12 years. Now she's back in the country freelancing. All of them are products of our data sciences. We run a diploma in data science and analytics, which happens every Sunday. Many of you know that. And when you go to the 3rd semester, you can actually get, some of you can get free admission to that data science analytics course. So they're products of that data science analytics course, and they use these, they do training modules essentially across various corporates, because corporates currently need that kind of data skills. You see, currently they pay a lot of money to SaaS. Most of the companies use SaaS, and SaaS costs a bomb. It costs them so much that most corporates actually outsource this. They send this data, such kind of jobs, to their head offices in the US or somewhere, where the data gets analyzed and it comes back. But they require people to have these skills, and these are important skills for all of us to have. So you are all welcome to be a part of that workshop. It will be a 4-day workshop, but you should reserve the full 4 days for it. Only those who can reserve the full 4 days for it are in for the workshop. You can't say come the half day on this day and the half day on that other day, because you will neither will you learn anything, neither will it be fun for us to teach. So if you're willing to allocate those 4 days to learning this, we will be happy to do that. And unfortunately, I can do it only during this 4-day break because it's a 4-day training module, and the other option is to split it on weekends, Saturday, Sunday, Saturday, Sunday. But then Sunday we teach our data science courses, Saturdays you have lectures. So this is the only opportunity really to do it quickly. So you will be there, some of your semester 3 friends will be there. How many of you have access to laptops? Okay. How many of you have no chance of getting a laptop from anywhere? Virtually no chance of getting a laptop. Okay. So what I'll do is I'll try to arrange some laptops for you. Some of us will share our laptops with others. There will be 2 of you writing the program and the code like that. Yeah. So please do come for that program. 7th, 8th, 9th, 10th. At the end of it, there will be a small, you'll also actually get a small certificate saying that you've successfully participated in this workshop. Yeah. So it will be fun. You'll actually be able to do all that we are doing in class. You'll actually be able to do that on a computer. Yeah. Sure? Okay. And please don't forget the lecture on the 2nd. Right? We are also planning a workshop. I'll tell you when the dates are there. The dates are to be finalized, but the panel discussion is finalized. It's a panel discussion on GST, Goods and Service Tax, and its implications for Maharashtra. Quite a few important people will come for that. There will be some economists, some experts from the department itself on Goods and Service Tax. Then we are the ex-finance minister of the government of Maharashtra, Mr. Jayant Patil will be a part of that. We are hoping that the current finance minister as well as could be a part of that discussion because it's an important discussion. But before that, just to prepare the ground for you, Dr. Mala Laravani, who works a lot on GST, will give you an introductory lecture on what GST is all about, so that you'll be able to understand that debate in a more nuanced fashion. Yeah? Thanks a lot. Sure. So now, if you remember, what we were saying yesterday was, these are N observations on X. This is coming from a normal population. Yeah, so what does this mean? How do you read this? And I will write here as IID. IID means independent and identically distributed. IID means independent and identically distributed. Yeah? What does this mean? How does one read this sentence? This says that x1, x2, x3, x4, x5, x6 and so on till xn is a random sample of size n from a normally distributed population which has mean mu and variance sigma square, which has mean mu and variance sigma square. So x1, x2, x3, xn is a random sample. Why do you say random? Because it's all are independently and identically distributed. So x1 is distributed with mean mu variance sigma square, x2 is distributed with mean mu variance sigma square, x3 is one observation from a population which is normally distributed with mean mu sigma square, and here x1, x2, x3, xn. Okay? Right? Sure. So now we thought of x bar. Yeah? We thought of x bar. What was the distribution for x bar? Normal. X bar was a random variable we saw yesterday. What is the mean of x bar? And what is the variance of x bar? Sigma square by n. Yeah? sigma square by n. Right. So, another important point now. Something that you have already learned actually, but now you also have a proof. Okay? What do I mean by saying that the variance of x bar is sigma square upon n? What do you mean by the variance? Variance means the average distance of an observation. Right? Okay. So what do I say? If I say the average distance of x bar from mu, so if I have a sample of size n, I can take different samples of size n. So I'll get different x bars. It will say, if I calculate the distance of each of these x bars from mu, it says the average distance of a randomly picked up x bar from mu will be sigma square upon n. This means as n keeps on increasing, sigma square upon n falls because the denominator increases. What does that mean? That means that as the sample size increases, the average distance of a randomly picked up x bar from mu will keep on falling. Which means that if I take mu, so think of x1, so think of x bar based on a sample of size 2. Think of x bar based on a sample of size 3. Think of x bar based on a sample of size 4. So on and so forth. Right? Okay? So you can think of x bar based on sample of size 2, x bar based on a sample of size 3, x bar based on a sample of size 4, so on as a sequence. Yeah, x bar based on a sample of size 1, x bar based on a sample of size 2, x bar based on a sample of size 3 as a sequence. Right? And what you're really saying is, if you think of mu, and if you think of any circle, any open neighborhood around mu, the probability that there always exists some n says that x bar upon n is within that circle can be made equal to 1. Because by choosing larger n, x bar n will get closer and closer to mu. So if I take mu, and if I take a circle of any radius around mu, I can always think of an n sufficiently large so that the average distance between x bar n and mu is within that circle. So the probability that x bar n lies within some epsilon distance of mu for any epsilon can be made 1 by choosing n sufficiently large. If any estimator satisfies this property, we say that it's a consistent estimator. So we have proved that x bar is actually a consistent estimator for mu, which is nothing but the law of large numbers. As n becomes large, sample mean gets closer and closer to the population mean. Right? The sample mean gets closer and closer to the population mean. And it's a very powerful theorem because we can use it for covariance, variance, all those kinds of things. So we saw how we can actually get the estimator for the regression coefficient beta hat. Because beta hat beta is covariance xy upon variance of x. We do not know what is covariance xy, but we know that summation xi minus x bar, yi minus y bar upon n is an average which will get closer and closer to the covariance xy as n becomes large. Similarly for the denominator. And therefore we can actually, if you think of the estimator summation xi minus x bar, yi minus y bar upon summation xi minus x bar square, it has the property that as n becomes larger and larger and larger, this estimator will get closer and closer to the true population value beta as long as covariance x and e is 0. Right? Okay. So now we've got this. X bar is n mu sigma square upon n. Is it clear? Okay. So if this is a normally distributed random variable, think of x bar minus mu. So what am I doing? From the random variable I am subtracting its mean. Like yesterday's example of subtracting the mean weight of elephants from the individual weights of all elephants. I divide this by the standard deviation. What is the standard deviation of x bar? The variance is sigma square upon n. So this is a normally distributed random variable minus its mean divided by the standard deviation. What distribution does such a normal variable follow? The standard norm, which would mean that this must be standard norm, right? Which means that the probability x bar minus mu upon sigma by root n less than equal to minus 1.96. Yeah, there is 2.5% chance that this value is less than minus 1.96 or greater than plus 1.96. So we get this. Okay. Now this actually is a very, very useful idea. I'll tell you why this is a useful idea. Okay. Why this is a useful idea. Suppose now I tell you that I have a sample. So this is a sample. Okay. This is some sample. If I tell you that this sample, maybe if I added some more numbers, from is add to 10, 13, 15, 18, okay, 18, and what is 18, say, yeah, so how much is adding up to? 27. How many options do I have? 9. Now suppose I tell you that this is a sample from a normally distributed population, yeah, with some unknown mean mu, and say a known variance equal to 4. Right? So this is unknown, this is known. Right? So make sure we understand what is known and what is unknown. In this problem, we know the population variance. Somehow, maybe a little bird came to you and told you that the population variance is 4. But somehow we know it, right? Okay? Mu is the unknown one. Mu is the unknown population mean. You have to make a guess at what the population mean could be. So I ask you the question, what do you think of the chance that this sample has come from a population with mean 5? What do you think of the chance that this sample has come from a population with mean 5? What do you feel? How will you use that? How will you think around this question? Do you think this sample could have come from a population with mean 5? You look at it and see it could not. Why do you think so? Yeah, but look here. You could actually have a population which is distributed like this, has a lot of variance, right? This is the mean. You could pick up some number here by chance, some number here by chance, some number here by chance, some number here by chance. So they don't necessarily, any of those numbers don't necessarily have to be equal to 5, neither do they have to be close to. Right? So what you need is a way of testing this statistically. You can't do it visually. So suppose we agree, we start by assuming that this sample, this population actually come with a mean of 5. You asked me to check whether it's 5. Okay, let me start by assuming that this has come from a population with mean 5. So I say, let that presumption be the null hypothesis. So mu equals 5. Mu equals 5. Alternative, mu is not equal to 5. Yeah? Okay. So, if this is true, simply by the process of filling in the blanks, this becomes, simply by the virtue of filling in the blanks, because you have told me mu is 5, so let me put mu as 5. I now know, because this is a normally distributed sample, the sample has come from a normal population, I know yeah, right? So now this assumption means that x bar minus 5, what is sigma? Sigma square is 2 upon what is root n? 3. Because that's why I thought it was additional numbers. Right? So that you could get a root which is easy to work. 2 by 3 must be a standard normal. Right? So if it is a standard normal, the probability, so probability you agree with this? So 95% of the times x bar must lie between minus 1.96 plus 1.96. 5% of the times it would lie outside these intervals. X bar minus that quantity, right? We will call this is generally called the Z score. This is generally called the Z score. Okay? Now what is x bar? The only unknown quantity there is x bar. What is x bar in this case? 3? Oh. So let me put 3 here. So what is the quantity that I get? So I get yeah? Now does minus 3 lie in the minus 1.96 plus 1.96 interval? Or does it lie outside this interval? Does it lie in the interval or outside the interval? Outside the interval. Yeah? What does that mean? It means that if the null hypothesis were to be true, there is a less than 5% chance of observing a sample mean of 3 given the population variance and the sample size. Right? Given the data that you have. What is the data that you have? The data, the known population variance and the sample size. So given this information that you have, the chance that mu is actually 5 is less than 5%. Okay? Now go back to the older example of elephants. So we have this elephant who is too thin. But is he healthy? Yes, less than 5% of elephants, healthy elephants will have a weight, less than that, whatever limit that we have put in. Yeah? So, if you call this elephant unhealthy, there is a chance that you are misclassifying some elephants, some healthy elephants into unhealthy elephants. Similarly here, if you reject now the null hypothesis that mu is actually equal to 5, there is a at most 5% chance of going wrong. There is a at most 5% chance of going wrong. If you are willing to take that risk and say that it's unlikely that this population could have come from, this sample could have come from a population with mean 5, because had it come from mean 5, okay, the probability of finding this Z score is too low, right? You would reject the null. Then you will be rejecting the null at 5% level of significance. Are we all getting this? Yeah? Sure. See, what have we found? What is our null hypothesis? Mu is equal to 5. What is it? It's a hypothesis. It's a statement whose likelihood we are going to test. What is it that we are going to test with? We have some actual data. We have a known sigma square and we have an n. This is the information that we have, and we want to test whether some hypothesis could be true, which is the hypothesis we cannot directly test. Yeah? So think of somebody who's been tried for murder. Nobody's actually seen that person commit murder, but there is some circumstantial, some evidence, and you're trying to see whether, given the evidence, can we, what can we make of the evidence? So we start with the null hypothesis that this person is innocent and try to see whether the evidence that we have makes it very unlikely that this person is innocent. Yeah? Okay, so similarly, because nobody has actually seen that person commit the murder. Similarly, we have no way of knowing what the actual population mean is. We just have a hypothesis. Because we can't study the entire population. Had we been able to measure the entire population, there would not